What's coming up within the next 30 minutes is that, of course, I will give you an overview on the platforms themselves, giving you some hints on some pitfalls which are there. Then how we did it, how we implemented drug resistance testing using the MySeq in our lab, and of course I will give you a very short case report on that. So let's get started, just to make everybody familiar once again with what's behind next generation sequencing. And this is what we use for a lot of years, standard Sanger sequencing. And you put all things together, just right around in the top, and then sequence it. Well, what you get, you will end up in a consensus sequence. And the opposite is done with the ultra-deep sequencing approach or the deep sequencing approach today. This is on a molecular level so that you can sequence each molecule, each virus virtually. So the players in the big game, you see right here, this is a very nice slide coming from Lex Nederbracht. And he was showing the evolution of next-generation sequencing or sequencing itself. And you see right down here, there's the Sanger sequencing providing you with sequence lengths of about 800 base pairs. And the first one was the GSFLX or the GS20 machine in the late last decade, or I think somewhere around 2005. And from that on, there was a tremendous evolution on that. And right now here in 2017, should be here right up, the what is called, Alex? The NovaSeq, yes, I think the NovaSeq providing you with terabytes of data. So what I would like to focus on once again are those platforms from which I think that they had already been used in the daily routine, which is the Illumina machine, or one of these Illumina machines. Doesn't matter whether this is the MiniSeq, the MySeq, NextSeq, or the latest evolution in there, which is the iSeq. Then the Ion Torrent here, and there are some other companies who use this in their instrument setup. And what I'm not talking about anymore is the Roche system, which is faded out right now, and the support was quitted 2 years ago. So the Ion Torrent PGM machine is based on a semiconductor chip right here with about several 100,000 of cavities where the sequencing process itself takes place. And this is the chip here, and I think the newest one is the 318 chip, providing you with up to 2 gigabases in output. The workflow is quite similar to that what we have had with the Roche 454. You have your library preparation, ligating your adapters on that. You have the template preparation on these spheres or the beads themselves, which is indeed an emulsion PCR. And you have the machine on here with a chip where the signal is deduced. In former times of 454, it was a typical pyro sequencing with light emitting. And here it's a change in the current or in the pH, which is measured. So you see right here, which is the 318 chip. It's very, very fast. The 200 base pair reads or 400 base pair reads, I think, will end up somewhere in between. With 300, 350 base pairs is done in 7.3 hours. And once again, will provide you with up to 5 million reads, which will yield in up to 2 gigabases output. The VELA next generation sequencing assay is using the Ion Torrent here, right here, and it is some kind of a carefree solution for everybody. So roundabout, all around happiness package. And what you can find within that is you have some kind of a liquid handler which is used for the sample preparation itself, so extraction of the RNA, and also for the library preparation, and for the library preparation as well, you have the Sentosa SX101 or the Sentosa ST401, which is doing the emulsion PCR, the machine itself, and of course you have your workstations for the analysis of the data. So, focusing here on the right column here, HIV it is integrated is the protease, reverse transcriptase, and the integrase. So V3 is missing, and it covers all major or all subtypes from the group M. So at least you will end up with more than 1,000 X coverage for the variant calling. You can use up to 15 samples per run. And you see the analytical sensitivity, because the PCR, RT-PCR is included, is somewhere around 1,000 copies per ml. So if you will use this in daily routine, you can end up in up to 60 samples per week. And I've heard they try to increase the number of samples per run up to 20, so which means that you can end up in 80 samples per week. So cost per sample is always an important thing. So when running a complete chip with 15 samples right now, you will pay for that 110 euros per sample. So Illumina platforms, to make that complete, we have a quite large family, and I'm just focusing here on those with a lower output, starting with the iSeq 100, providing 1.2 gigabases and going up to 100 gigabases with the Nextseq platform. I think most popular, which was the first benchtop sequencer from Illumina, is the MySeq, and it's quite variable, and, which is most important for us, it's able to provide you read length with up to 300 in each direction. So what's behind that? The technology, very briefly, it's just a coupling of the library on a flow cell, and by bridging PCR you are generating some clusters for amplifying the signal, and the signal at the end is deduced from a process which is called sequencing by synthesis here, in which all the nucleotides are coupled to a fluorophore, and which is then detected by a camera. So what is very, very easy is the library preparation itself. So we are in our lab focusing on the Nextera XT segmentation systems. Very, very easy, with hands-on time less than 50 minutes. What you can use, and which could sometimes the problem, is the outputs of the PCR, which here just you use 1 nanogram of DNA per sample. There are more than 380 indices available, so you can pool a lot of one run. And very important, what I think, is the normalization step, which ends up in a relatively homogeneous distribution of the reads. And here's the scaling. This is 1%, this is 2%. There are 60, 70 samples here on this flow cell, and you see this is like here a pearl. Okay, so third generation sequencing, or next generation sequencing, or whatever you will call it. We are of course focusing here right now on the Minion, and we have done some experiments within the last 5 years, when it was, I think it was 5 years ago, when they started with the project, the MAP projects, and this is really quite nice system. The output, which has up to 21 gigabases, in a 1D setup, which generates 400 bases per second in 48 hours. The read length depended on the fragment size, but the longest reported or ever reported read is more than 890 kilobases in length, which is quite a lot. The starter kit is relatively cheap, with $1,000 US, which includes 1 Minion and reagents for 2 run. And right here you see that it is a really tiny, small device here, and what you need is a relatively fast and good computer, and that's all. So this is the technology behind the Minion. There's a nanopore in a membrane, and the DNA is catched by some called motor protein, which is a helicase, so it's unwinding the double-stranded DNA and pushing it through the nanopore alongside here a detector molecule, and the change in the current is then measured and taken to the computer, and you will get here some kind of, they call it a flowgram. So we did some experiments on that with the Amplicon, just 1.3 kb in length, but we were able to generate more than 10,000-fold coverage of full-length Amplicon here with close to 1.35 kilobases. So unfortunately, we have seen that you can't use this in a daily routine, because at that time the failure, the error rate was extremely high, with more than 20% per position, which is really quite a lot. They improved the quality and the accuracy a little bit from the R7 flow cell to the R9, but we are still far away from that, what we should expect and what we need for HIV drug resistance testing. So if you still would like to do that using the Minion, you can apply some tricks like we did it and presented the data last year by circularizing the Amplicon, do a random priming and an isothermal amplification with a V29 polymerase, and at the end you will end up in concatenators of several copies, which should be identical, with a length of 80 to 100 kb. And for a bioinformatician, it's no problem to do then with these concatenate sequences, consensus sequences, and you will end up in a relatively high accuracy. After 6, 7, or 8 cycles, you're already relatively close to 80 to 98 or 99%. So an outlook for the Minion, and we had also already some approaches, but which were not that successful in direct RNA sequencing using this. And you can use a special Y adapter to the mRNA or to the RNA ends, but it's really relatively difficult to design these and be successful in the sequencing approach itself. So drug resistance testing using the Illumina MiSeq in our lab. So sure, we started with the V3 region with ENV, but it's no problem to add in the same approach the protease, reverse transcriptase, or the integrase, or if you don't mind, you can amplify the whole genome and put it in one reaction for the segmentation or for the fragmentation approach, which is done in our lab automatically, semi-automatically, using here a micro lab star from Hamilton, and this was, when I remember, the first Hamilton micro lab star, first time where the Nextera XT protocol was running on this machine. So putting things together, this is Alex's work, and he is doing this by mapping all the tiny little reads to a reference sequence, and then you will end up in the complete sequence. And we are focusing with regard to the coverage somewhere between 10 and 20,000 X. So the validation, what we have done was in parallel 400 samples for protease, reverse transcriptase, the NGS pipeline, and the Sanger sequencing pipeline, and in the end, the analysis. And we compared the data, of course, and here's coming what you are expecting. We had 236 mutations which were detected by the Sanger sequencing approach, and by applying a 20% cutoff, you will have 230, so it's less. So the Sanger sequencing cutoff is a little bit lower, and the more you lower the cutoff for the NGS approach, the more mutations you will see, and at the end you will end up almost doubled the number of mutations detected. So, which means how many virus is indeed relevant. So patient 1 had just 1,000 copies, and looking at 1%, you will end up in 10 copies carrying the resistant mutation. On the other side, a patient with 1 million, you have at least 10,000 viral mutants. So we still do not really know where the clinical cutoff for the interpretation of these minor variants really are, but we try to apply here some kind of a technical cutoff, which is on the one side 10%, in which we seem that it is most close to that what is given by the Sanger sequencing approach. And we did this here in a combinatorial way, in which we wouldn't like to lose any mutation with the NGS approach here for protease and reverse transcriptase. And you see by applying these, there's no mutation missing here with the Sanger sequence, no mutation with the NGS approach, but you will lose with the applying of 10%, so somewhere about 11 mutations. And this is also true for the reverse transcriptase, and when you miss 15 of these drug resistance mutations. So we can go a little bit deeper in this, in which we try to compare. This is a DNA, a proviral DNA approach. And you see somewhere here is the K103N. This is a Sanger sequencing column, and here's the 103N mutation. And you see it was detected with 10% in the NGS approach, and it was also detected in the Sanger sequencing approach. All others, which are here highlighted in red, they were not detected in a Sanger sequencing approach. Indeed, there are a few others, like here, the D67N mutation, and the L74V mutation, which were also detected with the Sanger sequencing approach, although they have less than 10% proportion of frequency in this approach. So, of course, when we are talking about those little percentages and frequency, we have to look for some pitfalls or possible error sources. And there could be, of course, somewhere in the RT-PCR errors and the recombination as well during the PCR errors in the library preparation, editing in Sanger sequencing. Sequencing errors are relatively low with the MiSeq itself, but also comparing RNA and DNA viable, so which means ApoBec3G mutations. And also the polymerase and RT enzymes you use do have an impact on the quality of the data, in which you see here the deviations from the main variant. And we tested a few of these combinations using the superscript or the one step ahead RT-PCR kit from Qiagen, and you see the lowest deviation are seen with the superscript in combination with the platinum TAC, and the highest deviations are seen with the Qiagen one-step RT-PCR kit and using the hotstart TAC polymerase for the subsequent PCR. So, a case report which should show that mutations as low as less than 1% may have an impact on the outcome. And this is the story of a patient who was initially treated with tenofovir, FTC, and rilpivirine. And what you see right here, the viral load dropped down relatively fast, and he was stable for several months on this regimen. But later on, once again, he failed with this therapy, and there was an ongoing replication, and we did not know why the clinician did not change the treatment, but it was for us the possibility, opportunity to do retrospective resistance tests, and this is here what we have done. So this was the first date of a failure with somewhere about 10,000 copies per ml, and we just saw the 138K mutation at 100%. So just 2 months later, the mutation is still there, but you see there's the 150F mutation as well as the 219R, which is, of course, somewhere in the noise, in the background of the sequencing, but it's already detectable. So, once again, 3 months later, there's the K70E additionally, and right now the 115F is present at 100% and the 219 mutation at 2.8%. And further, few months later, the K70E is present there at 100%, and this is true for almost all others mutation right there. And you see there's the linkage, also the 179L mutation, which is later on present there at 100%. So the detection of these minor variants at a distinct time could lead, with the ongoing drug pressure, of course, to 100% at the end of the failure. So how to interpret these data and how do we the interpretation with that? So once again, Alex did a great job on that, providing for us in the lab the deep type HIV report generator. And this is just the mass on the computer, and you see you have here two columns. You are uploading a frequency file, an AA frag file. And what you see here, this is the column right here for the patient identification and therapy data. And here in the two columns right here, all mutations are listed with a frequency at least with 10% or higher. And this column here on the right side includes all mutations which are present between 10% and 2%. So once again, here are all other mutations listed here, with the detailed information on the frequency itself, and you have here an additional data module. The newest release carries also an information on the coverage, which can be seen here down. So we have the tick boxes here for the visualization of the resistance situation from susceptible, limited susceptibility, intermediate, and highly resistant. You have pre-configured report components which you can use, and we also implemented is the HIV grade algorithm, and there are others incorporated like the RNAS, the HIVDB, and the Riga algorithm as well. So they can look in that at different cutoffs, interpretation cutoffs directly from the program. So which will end up in our report, showing here this tiny colored bar, once again with the information on the mutation frequencies, and of course there's space for comments, especially then when you detect minor variants. So costs is still an important thing, and just looking at those who are working with the Illumina MySeq with the 2x250 approach. So at 25 samples per week, you were able to sequence protease reverse transcriptase plus integrase plus ENV or whatever you want, and calculate the coverage with about 20,000 X, which will end up in the sum of less than 2 gigabases. So there's still a spare capacity for other projects of 6 to 7 gigabases, and this run covering all the reagents will end up in 92 euros per sample. So this calculation is based on the Illumina's price list in Germany in 2017. So what is not included, once again, is the biometrician. Okay, there are some things money can't buy. For the rest, you have your MasterCard. And this is the last slide when you have seen that the costs for sequencing has dropped down since the involvement on next generation sequencing approach down to a fraction of $1. But on the other side, you have to pay the bioinformatician, and I think this is a quite nice give over for Mark. Okay, that's it.